Hi everyone. Uh, since we have started our discussion on the frequency response and the transient response of op-amp based circuits, I thought it's the right point to introduce some very simple circuit analysis techniques to analyze these op-amp based circuits, mainly integrators and differentiators. Okay, so anytime if you are analyzing an op-amp based circuit, when you are performing a transient analysis, there are three zones of interest in time for circuit for the analysis purposes. So what are those? So I'm going to split the time axis, time scale into three different regions. The first region is what we can call as steady state before the switching input, which before the switching event. So here we are going to assume t equal to 0 is the point where the switching event happens, meaning a sudden transient input will be applied at t equal to 0. You may have a step input applied to this circuit at t equal to 0, or you can have an impulse input applied to the circuit at t equal to 0. So t equal to 0 is when the step input or the sudden switching event takes place. So then we can divide the whole time scale into three different regions. T less than 0 minus, and at the switching event 0 minus to 0 plus. This is very crucial in understanding circuits, and we saw in the previous example, in the previous lecture, a very interesting thing happened at this point. And then finally in the third region, that is 0 to infinity. So this is the point where the circuit settles, and then eventually at t equal to infinity it reaches the steady state. So if you see, there are two steady state events in this time zones. Okay, the first steady state event is at t equal to 0 minus. This is the steady state when the circuit is left to itself and a switching input is just about to be applied to the circuit. Okay, you're just going to apply a switching input, a sudden transient input. Okay, that's going to change the behavior of the circuit. So but t equal to 0 minus represents the time where the circuit is already reached some steady state. The other steady state point is t equal to infinity. This is where a switching event has already taken place, and then you have let the circuit to reach a steady state, to reach some final value, and then the outputs have all settled. And finally when you read the value, that is v, let's assume v0 of infinity is the steady state output value. So this is the steady state that has reached after the input, after the transient and the switching event has taken place. Okay, so there are two steady state points. Now in this lecture we'll try to take some simple differentiators and integrators and try to figure out, are there any rules, are there any simple design intuitions that are useful in predicting the behavior of the circuits at these 2 points, either at t equal to 0 minus or at t equal to infinity. So shown here are two integrators based circuits. So both these circuits are integrators. So for example, if I apply the input at this terminal or this terminal, if I apply inputs in here or here, both these circuits will act like inverting integrators. Okay, but I have grounded these two inputs right now, okay, in the circuit. Or if I apply the input at the non-inverting terminal, if I apply the input signal at the non-inverting terminal, both these circuits will act like non-inverting integrators. So that's why I said both these circuits are integrator circuits. Now you are supposed to find out what is the steady state output voltage. As I said, when I say steady state, it can be v of 0 minus. Before the switching event had happened, the circuit would have reached a steady state. You are supposed to find what is that steady state value, or some switching event must have taken place. Either the input has suddenly switched and then gone back to 0. So the other steady state is at v0 of infinity. I can use the word steady state for both these conditions. Okay, this probably a better word will be initial condition. V of 0 minus can be called as an initial condition, but I'll still call it as a steady state because the circuit has been in steady state for a very long time. So your goal is to find out what is this steady state output voltage. To find that out, it depends on the op-amp model that you are using. Now first I'm going to use an ideal op-amp model where the gain of the op-amp is infinity but the characteristics is saturating. Okay, the output voltage cannot go anywhere, it can always lie between minus Vsat and plus Vsat, and the gain here is infinity, right? So when the input is 0, suddenly the output can change from any value, from minus Vsat to plus Vsat. The other characteristic is the gain is finite, but with also saturating characteristics modeled into it. So the output will switch to plus Vsat if your input differential input, the input differential voltage, your V, just to recollect, V differential is given by V plus minus V minus. If this guy is greater than Vsat by A, then the output voltage will become equal, will be saturated to Vsat. Similarly, if your input differential voltage is less than minus Vsat by A, even then the output will be saturated to minus Vsat. So this is the characteristic, and you are supposed to find out what will be the steady state output voltage for assuming, for both these cases. So first we'll start with this circuit, a simple RC integrator circuit, and the assumption is the op-amp gain is infinity, but the output is saturated. The saturation limits are between minus Vsat and plus Vsat. Now remember, when the circuit is in steady state, you can treat the capacitor like an open circuit. You can treat it like it's an open circuit. Okay? If the capacitor is open circuit, there is no path for the current, therefore this input has to come to 0. The inverting voltage has to come to 0. Inverting node voltage, V minus, has to be equal to 0 because there is no current flowing through the resistor. There is no path for the current. If you make this assumption, now the differential input is exactly equal to 0. Now can you tell me, if the differential input is 0, what should be the output voltage? Will it be 0? Look at this transfer characteristics and say what will be the output voltage. Now if you observe this transfer characteristics, one thing you can notice here is that if Vd is 0, output can take a range of values. It can be anything. You can't precisely say what my output voltage will exactly be equal to. It can be anything. It can be any value between minus Vsat and plus Vsat. Your output voltage can be anything. Okay? Vd can be 0, but output can be any value between minus Vsat and plus Vsat. So the answer here is that we simply cannot say. It's not determined. Okay? So generally in such cases, if you are given a problem like this, then you have to look for what is the initial condition across the capacitor. This has to be mentioned. So if this is mentioned, if I already give you what is the initial voltage Vc of 0 minus, depends on the polarity of the voltage. So here I'm going to assume Vc of 0 plus. So this has the positive plate of the cap and this has the negative plate of the cap. So Vc of 0 minus is the voltage across the cap. If you are given the initial condition, then your output voltage will be equal to, here it will be is minus of Vc0 minus. Okay, it will be because the output voltage is measured at this point, and I have treated the plate, the capacitor's plate, which is connected to the inverting terminal, as the positive plate. Okay, which means that's at a higher, that's how I'm measuring Vc of 0. Okay, so in that case Vc of 0 will be minus of V0 of 0, V0 of 0 minus will be equal to minus of Vc0 minus. So all I'm saying here is that for this circuit, you cannot precisely say what the output voltage will be, and you can say if you know the initial voltage across the capacitor. So this information has to be given to you. Only then you can predict, and that Vc of 0 minus can be any value between minus Vsat and plus Vsat. Okay, that can be any value between minus Vsat and plus Vsat. So that's something for you guys to keep in mind. Similarly, if let's say I was given the inductor based integrator, even in this circuit, if you guys observe, in the steady state, the inductor's voltage will be 0. It will not have any voltage across it. Then this node voltage will come to 0. Again, Vd, the differential input voltage, is 0. So if you assume an ideal op-amp model where you have a saturating nonlinear characteristics with an infinite gain, then again you can't exactly say what V naught of 0 minus or V naught of infinity is. You can't precisely say what value it will take. If you have to know, if you have to precisely tell what value of V naught, the output, what will be the output voltage of this op amp, then you have to know the initial condition, which is the current flowing through the inductor. You have to know what is IL of 0 minus. If you know IL of 0 minus, then the voltage, the same current that flows through the inductor also flows through the resistor. So the output voltage in that case will be given by minus of IL 0 minus times R. Again, the inductor current can be of different polarity. It can be either flowing in this direction or this direction. Depending on that, the output voltage can be either positive or negative. So in this case, I have assumed the direction of IL 0 minus to be in this way. It's flowing into the inverting terminal. So this is the direction. So therefore, your V naught will be minus of IL 0 minus IL of 0 minus times R. Again, this value can be between any value between minus Vsat and plus Vsat. Okay, so that's the important point to keep in mind. So you cannot precisely say, you have to know what the initial condition is in these circuits. Now in the second case, I'm going to assume finite gain characteristics. For a finite gain characteristics, if you observe the op amp characteristic, the op amp's input-output characteristics has a very interesting property. The graph, the input-output characteristics, V naught versus V differential, has a unique one-to-one mapping between the voltages. That is, for every value of Vd between minus of Vsat by A to plus Vsat by A, the output voltage has a unique correspondence. So now, in the steady state, I'm going to assume capacitor will act like an open circuit. Okay, if the capacitor acts like an open circuit, no current flows in the circuit, no current flows to the resistor as well. Okay, there will be no current in the circuit, or the cap will be open, so no current will flow through the op amp from the output of the op amp. And similarly, since the input current into the op amp is 0, the current through the resistor will be 0. And therefore, this node voltage will exactly come to 0. And if you see, the differential voltage is exactly equal to 0. If the differential voltage is exactly equal to 0, then if you look at this graph with a finite gain, you can see the output voltage also has to be exactly equal to 0. So keep in mind, in this region, when your differential input is in this region, minus Vsat by A to plus Vsat by A, the output voltage is simply given by A times Vd. So there is a unique one-to-one relationship between the differential input voltage and the output voltage. Okay, there is a unique one-to-one relation. And so if Vd is 0, then V naught is also exactly equal to 0. So here I can clearly say V naught will be exactly equal to 0 for this circuit. Okay, so there is no ambiguity here. You can very clearly say that the output voltage will exactly be equal to 0 volts. Now, similarly in this circuit, if you assume the op amp gain to be finite, in the steady state, the inductor's voltage will be 0. This node voltage will be forced to be equal to 0. The inverting voltage, V minus, will be forced to be equal to 0 because inductor will not have any voltage across it in the steady state. It can carry a DC current without any voltage across it. So if V minus is 0, V plus is already 0, so the differential voltage is 0. Therefore, using the same argument as before, I can show that I can simply say that the output voltage will exactly be equal to 0. So in the steady state, for a differentiator circuit, if you assume that the op amp has a finite gain, then I can clearly say when there is no external input applied to the circuit, right, the other ends of the inductor and the non-inverting terminal are both connected to ground. then the output will be exactly equal to 0. So it's very useful. We'll see once we start analyzing more integrator and differentiator based circuits, you'll see all these principles will come in handy. Circuit analysis rules will come in handy. Now what about differentiators? The thing with differentiators is that the one distinguishing factor between differentiators and integrators is that if you guys remember the time scales, I drew a time scale unit and said that you can split this time scale into 3 regions. The time where the region where the switching takes place, and then the steady state region, and before the steady state before the switching event takes place. Now for integrator circuits, there is no DC feedback. If you observe both these circuits, right? If you observe both the integrator circuits, I'll probably show it here. Let me show the circuit here. Yeah. So if you observe both these circuits, the integrator based circuits, at DC this capacitor is an open circuit. So therefore, even if the output voltage changes, nothing is fed back. V minus will always stay put at 0 in the steady state. So there will be no feedback, no negative feedback in the steady state for this ideal. This is an ideal integrator, and we discussed before how do you, a practical integrator, we have to add a resistor in parallel to the capacitor so that there is a DC negative feedback as well. So, but leaving that aside, I'm just trying to tell you that this circuit, an ideal integrator, suffers from the problem of having no DC feedback in the steady state. You can apply the same rule here as well and quickly see that in the steady state, since the inductor voltage will be 0, this node, the V minus, will be forced to be exactly equal to 0. Because it is forced it doesn't matter what happens to the output voltage, this node voltage is V minus is forced exactly equal to 0. Because it's forced equal to 0, even if your output voltage changes, but if there is a DC change in the output voltage, there will be no DC change at V minus. So which means there is no DC feedback. So both the circuits, whether you build the integrator using an inductor or an RC or a capacitor, integrating circuit using a capacitor, both the circuits will have no DC feedback in the steady state. That is, at t equal to infinity and at t equal to 0 minus, there is no DC feedback. On the other hand, for differentiators, if you look at a differentiator circuit, the differentiator will have proper DC feedback in the steady states. So capacitor here, if you see, this capacitor will act like an open circuit and there is a perfect DC feedback. Okay, the resistor is feeding the signal back, output signal back to the inverting terminal. So it will act like a voltage follower. And similarly, in this case, the inductor will act like a short circuit in the steady state. So again, you can show that there is a perfect DC, it will act like a short circuit. So again, it will act like a voltage follower. Okay, so that's the one big difference between integrator and differentiator circuits. So keep this in mind. The differentiator circuits will have proper DC feedback when in the steady state. Okay, so anytime there is a proper DC feedback in an op-amp based circuit, you can precisely predict what will be the output voltage, what will be the output DC voltage. Very clearly you can say what will be the output DC voltage. So here then I can easily say what is V naught of 0 minus, which means I am letting the circuit to behave itself for a very long time. I am leaving the circuit to itself and then looking at the output voltage. So you can treat the capacitor to act like an open circuit, and then if you see, right, this circuit reduces to a voltage follower. So this node will be a virtual ground. It will perfectly track the non-inverting voltage and it will come to 0 volts. The other circuit here, the inductor based integrator circuit, the inductor will act like a short circuit in the steady state. Again, if you guys see here, there is a proper negative DC feedback. Output voltage is fed back to the inverting terminal, and therefore this V minus will also come to, so for if you guys remember, for if you assume the op amp's gain is infinity, V minus will be exactly equal to V plus, and that will be coming to 0 volts here. So I can very clearly say what the output voltage will be. And you can also show here for this circuit, the capacitor voltage will also be 0 in the steady state. Capacitor won't store any voltage across it. That will also be 0 here. And the inductor will also not carry any current. It will not carry any current in the steady state. The current value will flowing to the inductor will also become whether it is IL 0 minus or IL of infinity. I can show that in the steady state, okay, the IL of infinity or IL of 0 minus will be equal to 0. Why is that? If you assume any finite current flowing through the inductor. Okay, inductors can maintain a 0 volts across them and still carry a finite current. Then the resistor has to carry a finite drop across it. But since I have assumed the one of the inputs to the resistor is 0 and the inverting terminal is forced to be at 0 volts by negative feedback action, no current can flow through the resistor. Okay, and same current flows through the inductor as well. So therefore that current also has to be equal to 0. So the states of the circuit, so when I'm using the word state here, usually states represents different variables. State variables represent different nodes in the circuit. You can very precisely define what all the node voltages and currents in the circuits will be. Okay, and the same thing holds true even if you assume, so here if you see, I've slightly modified the circuit and I've applied a 10 volt input. Okay, instead of applying a 0 input here, instead of applying a 0 input, I've applied a 10 volt input. So even if I apply a 10 volt input, in the steady state, the capacitor will carry this 10 volt charge. The charge will be 10 times C. The voltage across the cap will be 10 volts, but the output voltage will come to 0. Okay, capacitor will store 10 volts across it, but the V minus will come to 0. There is a DC negative feedback, so output has to come to 0. And similarly in this circuit, if you connect a 10 volt at the input to the resistor, the same thing will hold true. V minus will come to 0 because there is DC negative feedback. In the steady state, V plus will be equal to V minus, and inductor will act like a short circuit, and the output voltage will exactly be equal to 0 volts. But the inductor current, IL of 0 minus or IL of infinity, that will be equal to 10 by R. Okay, it will be flowing in this direction. It will carry a finite DC current, and we know that inductors, right, ideal inductors don't need to have any voltage drop across them to carry a DC currents. So V of 0 minus will be 0, but it will still carry a finite current. So what you see here, even though I'm assuming the op amp to be ideal, all I'm trying to say here is that for differentiator circuits, these circuits tend to have proper DC feedback in the steady state. Therefore, you can uniquely find out what the voltages and currents are in the circuit in the steady state. But when you're analyzing op amp based integrator circuits, whether it's built using inductors or capacitors, you cannot clearly say what will be the steady state output voltages. For that, you need to know some more information, either initial voltage of the steady state voltage across the capacitor, or the steady state voltage across the steady state current flowing through the inductor should be known to you. Okay, if you know that, then you can precisely predict what will be the steady state output voltage. Now we can extend this and then argue. I haven't shown any plots here, but I can easily assume the op amp to have a finite DC gain. I can assume the op amp to have a finite DC gain, and then also show that, even if you assume the op amp to have a finite DC gain in this circuit, okay, so that is, the op amp has a characteristic that looks like this: saturating characteristic with a finite DC gain, a large DC gain but still finite. Even then, if you assume that as well, you can again treat the capacitor like an open circuit. There is no path for the current to flow. Since there is no path for the current to flow through the resistor, through the capacitor, the current through the resistor will also be 0, which means the voltage drop across the resistor will be 0. So your V0 will be equal to V minus. So your differential input will be exactly equal to 0. If your differential input is 0 and you know the transfer characteristics is to be looks something like this, then output voltage is exactly equal to 0. You can use the same logic, and for this circuit also, if you assume the op amp to have a finite gain, you can show the output voltage will also be exactly equal to 0 here. Okay, so we'll discuss more such circuits, but I thought this is a very useful point to keep in mind before we start analyzing more op amp based circuits. Thank you.